Welcome back to Quantum Field Theory 1, Lecture 3. So, last lecture we took a look at classical field theories, so I did like a short review on what a classical field theory is and what are the kinds of principles we'll use to build our classical Lagrangians, namely Lorentz invariance, and we'll see the Poincare group, right? So I try to convince you that you can actually, just by looking at representations of the Poincare group, you can build a number of different fields, each one transforming differently under the symmetries of the Poincare group. And the next step would be to quantize those fields, right? Because then we can look at, once I quantize those fields, what kind of physics will arise from that. But before doing that, we need a certain set of tools. We need a toolbox with which we will quantize those theories. And that's what we'll be doing for the next few lectures. So it will take some time before we actually go and quantize those fields, because we need to attack a number of problems before. So we need to develop some tools and apply them to simpler systems. So the first tool we will be talking about is functional integration, or path integrals. Right? This is a way that we can use to quantize theories, which is quite different from the canonical quantization, but it is completely equivalent in the end. You get the same quantum theories when you quantize them by using path integrals. So I will start describing what a path integral is in some simple examples, and then we'll take a look at the harmonic oscillator. So I'm going to the simplest and yet more complete example of quantum systems, and we'll take a look how would we go about quantizing an harmonic oscillator, and how can we compare canonical quantization with path integral quantization. So that's the plan for the next few lectures. For this subject, I recommend taking a look at Ryder's book on quantum field theory, section 5, because Ryder does the whole quantization of fields in terms of path integrals, and this section has a good review on it. Let's start by imagining a transition between two different quantum states, written in this way. So I have a wave function which I'm looking at point q prime at time t prime, and I'll write this quantum state in terms of a transition from a previous one. So I have this f of q prime t prime qt, and another wave function that I'll call psi of qt, and I'm integrating over q. I'm just trying to imagine a very simple one-dimensional example. So what's written in this equation is nothing but that if I start with a certain wave, right, with a wave function, this is how each point of that starting wave can influence, right, this point of the final wave, right? And I'm integrating over all the points because there's a transition for each of those into the final one, right? I have to integrate over all of them. If this is too confusing, you can imagine the simplest case where this is a very well localized wave, say at a point q naught. So this is just a Dirac delta function, and then this simplifies, right? Then psi of q prime t prime is just f q prime t prime q naught t. And since this is the probability of finding the particle at point q prime at time t prime, then this is also the probability that the particle that was initially well localized at q naught transition to this other point. So given that it started at q naught at time t, what is the probability of finding it at q prime t prime after some time, right? I'm assuming t prime is bigger than t. So this guy f, this function f, we call the propagator, and it gives this probability of transition from one state to another quantum state. Now we want to work on trying to obtain this expression for this propagator in terms of quantities we know. So let's consider first the wave function written in terms of brackets in the Schrödinger picture. So we know that phi of q t can be written as, here I'm using s to indicate that I'm considering states in the Schrödinger picture, right? Which means that the states themselves are evolving in time, but the operators are not, right? And this wave function is defined as the projection of the quantum state psi at time t on the eigenstates of the position operator, right? Both at the Schrödinger picture. And I can change from the Schrödinger picture into the Heisenberg picture, where the states themselves are not evolving in time, but the operators are, by doing this relation, right? And this is just the Hamiltonian operator for the system I'm considering. This is the time, and this is psi in the Heisenberg picture. So this state is not evolving in time. This one is, and this is the explicit time evolution, right? Now we want to define what is called a moving frame, which is a Heisenberg picture state, which I'll label as psi comma t. I'll keep the h here to remember this is a Heisenberg frame state that is written like this. And here is the position eigenvector at time t in the Schrödinger picture. So I'm just taking a sorry, I have to put Q here, right? Because I'm just taking a state that Schrödinger picture evolving is the opposite of this, and this is I'll call the moving frame, because I'm keeping this index 2 to remind me that this is an eigenstate of the position operator at time t. After I let the time evolve, the position operator will evolve in time in the Heisenberg picture, and this will not be an eigenstate of the position operator anymore. It is only at time t, when I use the position operator calculated at time t, that this is an eigenvalue of the position operator, right? So I hope that's clear enough. And I want to write the propagator in terms of these moving frame states. So in terms of these, I'll just take this expression and rewrite it as psi s q t, and this guy now I'm using this expression, which then I can absorb here using this definition and write this again. Now it's Heisenberg picture, q t psi h. Right? Now I want to calculate this guy. I also press the h on the left here, so if I'm indicating a bracket and there's only one symbol, that means both sides of the bracket are being calculated in the same picture, right? It's written in the same picture. Now, an object of this sort can be written like this. Let's take a q prime, t prime, psi in the Heisenberg picture. I can rewrite this guy by just inserting an identity here. I take the completeness relation for these eigenstates of the position and insert it here. If I do that, I'll get an expression that relates this wave function with another one, right? It will become q prime t prime bracket with q t. This is all this moving frame Heisenberg picture states, q t with psi dq, right? I've just inserted this identity there and got this expression. Now this, we know that that's what we shown here, right? It's just psi of q prime t prime. This one is exactly what's here, it's just psi of q t. And so this guy in the middle here, because we're getting the same equation that is up there, right? This is exactly the same equation. So this guy must be f, right? It's doing exactly this, getting me the transition amplitude from here to here. So this is the first thing we wanted to know, is that f q prime t prime qt can be quite simply written as q prime t prime qt, these moving frame states, which also can and will be useful to do that, sometimes written as q prime exponential of the Hamiltonian of t prime minus t q. Now this Schrödinger picture states. So this is how we can write the propagator. Now let's see how we could calculate this in terms of what I'm calling the path integral. Let's see what is the idea of the path integral. First, consider that we divide. We're again looking at this transition between t and t prime. Let me just organize it a little bit here. So this is what we want from this part. So we're calculating this transition between t and t prime. Now consider that what I can do, I can always do, is divide this time axis into many slices. So this is t prime, which is bigger than t by construction, right? And I'm calculating this transition, But now I want to introduce many intermediate times. Right? So I'll call this one t0, which is the initial, it's just t. But I also insert a t1, t2, and so on, until a tn. So I inserted from 1 to n new times in the middle here. I'm just considering these new times. And of course, t prime will be tn plus 1, because I inserted n times in the middle, right? The interval between any two neighboring points in time here we'll call epsilon. And of course, epsilon is just t prime minus t divided by n plus 1 slices, right? So I have n slices up to here, and n plus 1 is this last slice here. Huh? Okay, so, and then I can also write these times, of course, as t0 is just t, t1 will be t plus epsilon, t2 will be t plus 2 epsilon. So I'm assuming these are all equally spaced points in time, and tn plus 1 will be t prime. So I'm considering all this intermediate set of states. We know that for any time, right, there's a completeness relation, right? Whatever is ti, right, this time, there is true that the integral in position calculated as ti, which I'm labeling qi, but is really I'm taking all positions possible at this time, right? Of qi ti, qi ti. This is 1, right? By completeness I mean, basis using the eigenvectors of the position operator at time ti, I can write this expression. And to make the notation a little bit more simple, I'll suppress all these indexes and just call qi ti as qy. But it's really implicit that it is the time at which I look at the position operator that determines which are its eigenvectors, and this is the base I'm talking about. Right? Now I can take this expression for f and insert all these identities right here. Right? I can insert this identity for t1, then for the one for t2, then t3, and so on and so forth. I can insert n identities in the middle here. This will still be true, right? And f will be now written in a very special manner, right? So f of q prime t prime qt will be written as the integral. For each of these identities, I get an integral in a particular q. Right? So I'll just write this as dq1 all the way to dqn. At this point, it's important to notice that I'm not integrating in q0 nor qn plus 1, because this initial expression for f had those guys fixed. Right? I'm only inserting identities for the times in the middle, and that's where the integrals are coming from. Then I have, of course, what I had already, q prime t prime, and then all the identities, which I write in a different color. So the first one is qn tn, then of course qn tn, And then it goes all the way to, say, let's take the last two, Q2, T2, Q1, T1, Q1, T1, and finally what we had before, which is QT, right? One important thing to notice here, I inserted those identities in an ordered way. So you see the times are growing here in the same way I ordered them at that line at the start. Right, so I have transitions between times. There are first neighbors here. So transition from T to T1, T1 for T2, then I would have T2 to T3 and so on. Right? And I have all these integrals. That means I'm basically describing my transition from T to T prime in terms of many other small transitions. So essentially, let's say I just put 2 times just to be able to draw a nice picture. I'll put Q over here, and the time goes this way, and I'm calculating the transition from T to T prime. And just for the sake of simplicity, I'm inserting only 2 times, so n is equal to 2 here. That means I inserted a time T1, I time T2, T2. Let's assume this is equally spaced, so I have epsilon space in between them. And now, how would my transition look, right? So this point is fixed, right? That's what I want to calculate. I want the particle to have started at Q, position Q at time t. This is also fixed. Let's say Q prime here at time t prime. But these two are being integrated, right? But for any particular point in this integral, what I'm doing is take Q1, defined at time 1, Q2 here. What I am really calculating here, these many brackets, is our transition amplitude, say, from Q to Q1, and then from Q1 to Q2, and then from Q2 to Q prime. These are the propagators I'm calculating. When you look at this, it's easy to realize that what I'm calculating is a particular path that leads from Q to Q prime. In fact, I'm calculating all the paths because one must remember that I'm also integrating on both Q1 and Q2, right? So I'm also taking into consideration, say, points that Q1, paths where Q1 is here, Q2 is here, and this path is also taken into consideration. In fact, it was summed, right, by the integral. It was summed to the previous path. Also, you could have other paths, right, like this one, right? I'm adding over all these paths, actually integrating. Right? Now try to imagine what happens when I take the limit where epsilon goes to 0. Right? Essentially, I'm putting an infinite number of intermediate times here. Then I'll have these actual trajectories that take me from Q to Q prime, and I'm integrating over all the possible different shapes these trajectories can have. I'm essentially taking every possible path from Q to Q prime and adding them up together to get the final amplitude, right? Each of these paths will, of course, have a different probability, But that's what I'm doing, and this is what we call the path integral. So let me define a little bit of notation here. I use this capital D to indicate the symbol of integration for this huge number of integrations I'm doing, right? When I take epsilon to 0 and I insert a lot of intermediate times, I'll have a lot of integrals here, right? So the product of all these integrals going from I equal to 1 all the way to n of dq of I mean, I'm indicating qi there, but I want to be more formal here. I mean, just put a ti, right? All this huge product, this product of a huge number of integration measures, I'll call by this capital D, and the resulting integral I'll write like this. So this is the same I have here, but now I have a product of a big number of integrals. And one has to remember that essentially what I'm doing, right? Each of these paths is basically a function q of t, right? Once I take all the points on any particular trajectory here, I'll have for each time t an associated point q. This is a function, right? And I'm essentially, by doing this this procedure, I'm getting all the possible forms, all the possible functions between q and q prime. So this is an integral over function. So that's why we call it functional integration. Path integral becomes clear by looking at the fact that we are summing over paths, but also functional integration means we're integrating on the space of functions over many different functions that you could have, all the functions I can draw between q and q prime, right? That's what you're doing. And you could do that too. I mean, I'm doing a path integral for the position in terms of the time, right? But I could also do it for the momentum, So that's easy to see. I can even go from one into the other, right? We know that if I project position eigenstates into momentum eigenstates, I get this exponential, and that means that I can relate those two over by Fourier transformation. All I have to do is to insert here a completeness relation for the momentum eigenstates, and I'm using here this convention of putting the 2 pi on the Fourier transform together with the momentum integration. So that's the way I'll use my Fourier transforms. So using that, I can rewrite those transitions, each of those small transitions that we had before. These ones, right? You had these transitions between q1, q2, q1, qn, q prime. I can write any of those in terms of momentum. So what you have to do is take any of those qi, ti, qi minus 1, ti minus 1. And bring explicitly the time evolution, right? So this is, again, moving frame. I can go to, so it's Heisenberg picture, so I can go to the Schrödinger picture and have q of ti exponential of I minus epsilon Hamiltonian. The epsilon here is the time ti minus ti minus 1, but of course all the spacing between times is always epsilon, so I just put an epsilon there, And here I have Q of Ti minus 1, Schrödinger picture now. And I can insert this completeness relation for the momentum. Actually, I want to insert it here. I can take the identity written in terms of the momentum, which is just pi 2 pi Ti. Again, I'm using the momenta at a certain time, so I'm putting the index in the momenta just to make notation simpler. Pi Ti Pi Ti. Well, I can insert this identity here, and what I'll get is that this expression here becomes this, right? So I have to just arrange things a little bit here. And of course I have also the integrals here. So now I have also these momentum eigenstates inserted in the middle here. So this is easy, this is just an exponential, right? This one. But I have to deal with this. In order to deal with this, I have to remember that really this exponential of an operator is defined in terms of a series, right? Power series in h and epsilon, but epsilon is a really small number, right? Because I'm taking the limit where I have an infinite number of time slices in the middle, so the interval between any two time slices is going to 0. So I can forget quadratic powers of epsilon. So I can calculate. Let's spend some time just calculating this guy. Let me bring it down here. And what I'll really calculate is this. Which is the linear term in the Hamiltonian, because epsilon is small, and so that's good enough. Let me just leave some space here and put this guy over here. Now we know that Hamiltonian is a function of these two operators. Right? One of them can easily act to the right and become its eigenvalue. The other one can act to the left and become its eigenvalue. But of course, to be able to act with the momentum operators to the left and the position operators to the right, when I look at the Hamiltonian, the position operators need to be to the right of all the momentum operator. Otherwise, they cannot go through each other to act on the brackets, right? Of course, any Hamiltonian that can be written in terms of powers of P and Q can be ordered in this way, right? You can use commutation relations to move the Q's to the right and the P's to the left. And until you, of course, you get your complication will look, your Hamiltonian will look ugly, but in the end you have an Hamiltonian that is ordered in this way. This is called Weyl ordering, and it can be done. Right? So I'm assuming I do that with the Hamiltonian, and then I act with the operators. When I do that, I can basically remove all these operator symbols from here. And since this is Schrödinger picture state, when I act with the operator that does not change in time over there, I get the eigenvalue. So this becomes P Ti, and this operator Q becomes Q of Ti minus 1. And there's another parenthesis here that is coming from this one. Right? Now that I exchange the operators by values, right, I can take these out of the bracket and put back this very short series in terms of a exponential, right? So I can write out here just the exponential of minus I epsilon h of P of Ti Q of Ti minus 1 times Pi Ti Q of Ti minus 1. These two I are redundant, but probably just keep it like that. This second part is just an exponential, so I can rewrite all of these just as this first exponential times another exponential of minus I P of Ti times Q of Ti minus 1. Right? Now I have to go back with this to the expression above. I'm trying to calculate this expression for the one of those transitions. I already did this part. I also have to do this one. So let me take this down here. What I'm calculating is the transition to Qi Ti, starting with Qi minus 1 Ti minus 1, and I wrote this in this way. This first expression is here, so I can just remove this part and substitute by this one. And this is just another exponential. So this is just the exponential of minus, or actually the exponential of I Q Ti P of Ti, right? So I will substitute this here. And I will group the terms in these exponentials. Especially I want to put these two together, which takes me to this expression. So these two exponentials I'll put together, right? They have Pi in common, but the Q, here's Q of Ti, this is Q of Ti minus 1, and also they have opposite signs for the Q's. So I'll write these as P of Ti times Q of ti, which is this term, minus, because of this sign, q of ti minus 1. So I have this exponential here, and this one is just repeated, doing nothing here. And now I have to go back to the propagator, right? The propagator has a lot of these transitions in it. So let's take a look at the expression we had for the propagator. This one, let me copy it, take it down here, and now each and every one of these elements can be written in this way. That's what I'm doing here. Will become pretty big pretty soon. So let's do it. So now I have integrals over position. It's a product going from I to n of dq of ti. So this takes care of all of the position integrals. Notice that I have n insertions that gave me these n integrals, but I have n plus 1 elements to calculate because I had already the initial one, right? So I have one more integral in momenta. So the integrals in momenta, I'll use j. They go to n plus 1 dp of tj over 2 pi. Each of these integrals comes with a factor of 2 pi. Let me put these in brackets just to make things more clear. I have all these integrals. And I have a lot of elements like these ones. So let me first, for each of these brackets, I'll have one exponential of this kind and another one of this kind. Let me start grouping the ones of this sort, right? I'll have a product of all these exponentials, which I'll just write as the exponential of I. And I'll just make the sum of all the arguments in the exponential. So I start with p for this first term here, right? This is what I call, remember, q prime or t prime is my tn plus 1. So I just call p of tn plus 1 times q of tn plus 1 minus q of tn, right? This term right here, but for the last slot, this is q of n, and q prime is q of tn plus 1. And this is a sum that goes all the way to the first element here, which is just p of t1 times q of t1 minus q of t0. T0 is t. And this is what is on top of this exponential. Of course, this is multiplied by another exponential, this one, that has minus I epsilon times a sum, again, of terms like this one, like this Hamiltonian here. Again, starting from the last slot where the Hamiltonian is written in terms of t of n plus 1 q of n, and this goes all the way down to the Hamiltonian of p of t1, actually t0, q of t0. Sorry. P of t1, q of t0. Right? They are different. So this is the expression now for these two exponentials are multiplied here, and everything is inside the integral. So this is the expression for my propagator. Now what happens when I take the limit of epsilon going to 0? Before doing that, I want to do a little trick here. Let's multiply this exponent here by epsilon and divide by epsilon. So what happens when now I take the limit of epsilon going to 0? First of all, these become these integration measures here. They become the path integral, right? So this will become capital T dqt, and this will become the path integral in momentum. And it's, by convention, we include this 2 pi inside the integration. So I just write pt, right? I could put a 2 pi over an infinite number of 2 pi's here. You see the problem there. We'll come back to the 2 pi elevated to an infinite number later, but by convention I include this 2 pi inside the definition of this symbol. Right? And then there's all these exponentials. Right? So the first thing to notice with the exponentials, let them already put an I here, is that now this difference between say tn plus 1 and tn here it's just negligible, right? I just calculating this Hamiltonian at equal times for momenta and position, because this time is infinitely close to this one. The only place where I have to be careful about bringing these 2 times together is here, right? Because now I'm taking this to 0, but on the flip side, epsilon is also going to 0, right? Because this is just tn plus 1 minus tn, but you recognize here that I have the definition of the derivative for this function q of t. So what this becomes down here, this epsilon becomes just the measure of integration. This is just a small time interval, and the sum that I have over all these terms becomes an integral. I am summing over the same term again and again and again. So this is becoming the integral from t0 to tn plus 1, t to t prime, of dt is just epsilon here and here, right? Of pt, which is just this, times q dot of t, because this is the definition of the time derivative of this function q of t, minus the Hamiltonian of P and Q. And this is quite amazing, right? Let me separate this from rest. This is quite an amazing expression. Right? Because essentially I'm writing a quantum object in terms of expression that does not involve any operators anymore, right? It has this very strange infinite number of integrals, but this Hamiltonian is just a function, this is another function, this is another function. So the first thing I want you guys to notice is that P and Q are not operators in this expression anymore, right? We'll come back to that later. This expression is very useful, very general, but there's these two integrations. In most systems of interest to us, we can actually get rid of one of those. We can actually get rid of one of these integrals and get a simpler form for the propagator. In particular, I'm talking about systems where the Hamiltonian can be written as just a kinetic term. This is simplified. I'm assuming the mass of the particle is 1, but the important thing here is that I have a quadratic term in P plus a potential that only depends on the position. For systems that can be written in this way, I can actually simplify this expression by doing the integral in P in momentum. Right? I can substitute this expression here and write that f q prime t prime qt is just path integral over q, the path integral over p, exponential of I t to t prime. This is a normal integral on time. P q dot minus p square over 2 v of qt. Right? So I can integrate in P. This is a very general type of, very complicated type of Gaussian integral, right? I'm integrating in a quadratic P here. There's P squared plus term. I have to essentially do a Gaussian integral, but of this new crazy functional integral. So in order to get to that, I'll make a mathematical interlude here. Let's spend some time talking about Gaussian integrals, and then we'll come back to this expression. Okay, then let's remind a thing of two about Gaussian integrals. So the Gaussian integral we all know and love is the following, right? So if I integrate from minus infinity to plus infinity, the exponential minus alpha x squared, the x I get square root of pi over alpha, right? So this is the usual Gaussian integral. I trust everyone seeing this video know how to get this. We could take this and take the square of this expression, right? In this case, I squared is just twice this integral, so change variables from x to y on the second one of them, and write dx dy exponential of minus alpha x squared plus y square. This is the square of the left side. On the right side, I guess just p over alpha. This is pretty straightforward. I could also use two different alphas here, one for alpha x and another one for alpha y, and then I would have square root of pi over alpha 1 times square root of pi over alpha 2. Right? In fact, now let me do this n times. So now I'm interested in many Gaussian integrals, right? So I'll just number the variables dx1 to dxn, and the exponentials. Now I use one different alpha for each of these integrals, and I'm exchanging alpha for alpha over 2, just for convenience. You see why I want this factor 2 later. So I will just write minus half. This is the factor 2 I mentioned, and I have a sum alpha I xi square. So now I have n integrals like this one. I'm just putting I and I here, and you see it's the same. So I have just a product of many square roots. This is the factor 2 of the alpha, right? Over alpha 1 all the way to square product, right, of many factors, just like this one, all the way to alpha n, and that I'll write just as a 2 pi to the power n over 2 over a product over the index I of all the alpha I square root of alpha I. Right, so this is what I get if I have many Gaussian integrals. Right? There's a convenient way of writing this expression here, which is to put all these alpha i's in a matrix, right? So I could just build a matrix. I'll call it A, which is just a diagonal matrix with the alpha I in the diagonal, alpha 1, alpha 2, so on and so forth, until alpha n. This is just a diagonal matrix with the alpha in it. And I can build a vector x that contains all the integration variables, also order in this way, of x2 all the way to xn. And then this scalar product of x with ax will be just x I aij xj. Again, I'm using the convention that the repeated indexes are summed over, and this is the product with x with ax, which is exactly this, right? It's exactly what I have here. This is just the sum I to n of alpha I xi square. So that is good. Also, right, the determinant of this matrix, since this is just a diagonal matrix, right, the determinant of this matrix is just the product of the alphas. So this is just this product, almost. I mean, this is not the square root, but it is the determinant of this product, alpha I. So written in terms of that, I can just write these general, many Gaussian integral expression as just integral over a vector with in a n-dimensional space. It's just a vector in this space with n dimensions of the exponential of minus half of x ax, right? Scalar product. which is 2 pi to the power n over 2, right? And the determinant of a to the power minus half. Right? So now I wrote everything in terms of these matrix with the alphas in there. Right? See that once I write the expression like this, this is a good expression for us. Because since I write the expression like this, I can actually, the x are just integration variables, so I can rotate x's in this vector space here and get to any matrix as long as it is a diagonalizable matrix. Any matrix that I can diagonalize can be plugged in this expression with the same answer, right? Because the x's are just the basis for this matrix, so I can rotate, get it diagonalized, and prove this expression. But it is true even for non-diagonal matrices, as long as they can be diagonalized, right? And this is one of the important results we want, right? The second one, I want to also, so this is a generalized Gaussian integral, right? I have a square on the x, and I'm integrating. But also I want to be able to do Gaussian integrals in the cases where the x square is not perfect, right? So cases where the integration variable, I mean the exponent there, is not just this piece, it's not just this, this is actually the transpose, but also I have a linear term. I also have this linear term here. Let me put the transpose here just to be very rigorous. Okay, so now I want to know how to do this. Let's think of this exponent like an action, just to guide our intuition, right? It doesn't need to be, but just to guide our intuition. If this guy was an action, there's a particular important point of this function, which is the extreme point where the derivative of s is 0. Right? If this was an action, that would be the classical trajectory for a system controlled by this action, right? So if we, but what is important for us is that this is a extreme point of s, right? Either a minimum or a maximum. So if I take the derivatives towards x I and force it to be 0, right? What do I find here? Right? Let's see. So I'm putting this in here, writing it explicitly in terms of the indexes now. Aij xj plus bixi xi, and if I take the derivatives here, I'll have a half delta, this is a Kronecker delta, delta ik aij xj plus half of xi aij delta jk plus bk equal to 0. I can solve this and get that half of akj xj plus half of aik xi equals minus bk, and assuming A is symmetric, right, which is true if I diagonalized it, right, I can put these two terms together, right, just rename j for I and put these two together, and then I'll have that a x, let's call this xc, because this is the solution to this equation, right? It's just not just any x equals minus b, right? Which means that this xc will be minus a minus 1, is the inverse matrix to this one, b, right? This is for classical, because if this was an action, this would be the classical solution to the principle of this stream action. So, but the point here at this moment is that it is a minimum of this action, right? Because it's a quadratic action with positive positive quadratic term. So now, why is this useful? This is useful because if I calculate S of X classical, right, and I just take this solution and plug in here and do all the calculations, right, this term right here will be half of minus a minus 1 b transposed times a times minus a minus 1 b plus b transpose times minus a minus 1 b. So you see this, when I transpose, we have just, there's a lot of signs here. Let me get rid of the minus signs. This goes away, right? This will be just b transpose I minus 1 transposed is itself, because I'm assuming A is, this matrix is symmetric, right? So A minus 1, A minus 1 will be just A, right? And B. So this will be the same as here, but with a different minus sign. So in total, I have minus half of B transpose A minus 1 B. So that's what S of X classical is. But that means I can write the full function here, this action here, in terms of that minimum, because this is just a parabola. So I can write the parabola in terms of the minimum plus a quadratic term going away from that minimum. I can always do that, right? So that would mean I can write my action, now the full action, just as a quadratic term, but now instead of x, I write it in terms of this variable, which is x minus x classical, so it's going quadratically away from the minimum. plus the minimum itself, which is given by this. This is just another way of writing the same expression. If you don't believe me, all you have to do is take xc, substitute here, and you'll see that after a little bit of manipulation, you'll get up there. Right? It's very easy. Right? So then if I go back to the integration of exponential that involves this expression, right? Now I'm thinking about this integral. The nx of the exponential of minus half of x transposed ax plus b transposed x. Then I can rewrite this as the integral of exponential of minus 1/2 of x minus x classical. This is the minimum of that function that I had there, transposed a x minus x classical, right? Times exponential of this part, but this does not involve x at all. So it can come outside of this integral, right? I can actually write it out here as the exponential of minus half b a minus 1 b. And of course this integral, remember x c is just the minimum, so it's just a fixed x. The integral is really on x, and if I want to make a change of variables from x to x minus xc, I can do that and I'll get nothing here. So this integral is just a Gaussian integral as normal, like the one I shown above, right? So this whole expression will be 2 pi to the n over 2, the determinant of a to the power minus 1/2, and the exponential of, oh, I miss a sign here. You see the action was defined positive at the start, but I put a minus here, so this is plus, and this is exponential of half of b transposed a minus 1 b. So let me copy this just to have this very interesting closed expression here for this multi-dimensional Gaussian, right? So the effect of having this linear term is to produce this, and of course right from the start you see that this is only possible if this matrix here is diagonal and it's also invertible, because I took the inverse of A here. So you have to keep that in mind, right? So let's go back to our previous expression. So going back to the physics, this was the object I was trying to calculate, and if I pay attention only to the momentum integrals and the momentum part of these exponents here, what I have is really a product of integrals. I'm writing again the path integral explicitly, so this will be a product of these integrals in momentum. So I have the pi of the I mean, can just use one I over 2 pi. So there's a product of many of these integrals times the exponential of I. I'm discretizing this again, so it becomes the sum of epsilon, or I, the sum of epsilon of p ti q dot ti minus half of p ti square. So this sum makes this a scalar product between this vector and this one, right? Same here is the scalar product with itself. So I can compare this expression with the one I had before. I just shown for the Gaussian integration. So I can compare this with that and see that essentially my vector here x I will be just the p of ti, right? This is the quadratic part here, right? There's no, you see there's quadratic term in p but no a. That means that a ij is just a delta I epsilon to incorporate these two terms, right, that are multiplying this guy. The minus 1/2 is already included in the original definition, so this is just I epsilon Kronecker delta of delta ij, right? And b, which is the linear term, is just these, and you have to include the I epsilon too, so this is just minus I epsilon q dot of ti. And finally I have to get the inverse of this matrix, which is easy, right? A minus 1 ij is just minus I over epsilon delta ij, right? So then I can just plug this into the right side of this equation and write the answer for this integral here. So which will be, so the answer for this integral will be just let me collect all the numeric factors that go here. So I have a 2 pi to the power n over 2, but I also have a 2 pi to the power n coming from this part, right? This is repeated n times because this goes from I into n, right? So in total I have a 2 pi n over 2 in the denominator. In the numerator I have this determinant of a, which is just an n by n matrix, right? So determinant will be just I epsilon to the n, and then I have this power minus 1/2 out here, so this will be just I epsilon to the power minus n over 2, right? The n is coming from the determinant of this matrix. And then I have this exponential, right, which is just the exponential of I. Then I have to put these b's here, these. You see I have a cancellation, some powers of epsilon. So I have 2 powers of epsilon in the numerator, 1 in the denominator. I have just 1 in the end. Right? I have a sum. These scalar products will become integrals when I take the continuum limit. So I go back to the integral from t to t prime dt q dot of t square over 2, right? This is the q dot square is coming from the 2 b's here, and I just use these to sum them up, right? The rest is just numerical factors which are easy to figure out. So this is the result of the path integration of p. can actually do these integrals, right? I just have to plug now these back into the expression of f, and I'll get, let me write here, f q prime t prime qt is just some normalization. This normalization is tricky, right? This is the number that I have right here. Right? So this is n. Let me write in that color because... And I can understand if people are suspicious of this number, right? Because, I mean, there's a very big... n is going to infinity, right? So there's a very big number in the denominator, potentially another one, which is this epsilon to minus n here, right? Epsilon is becoming small, but it's a negative power. There's also a complex number here as imaginary number to a big power. So for now, we just keep this as it is, right? And we'll worry about this normalization here of this amplitude when we need, right? If that ever shows up in any observable thing, then we'll worry about it. By the way I'm talking, you're probably guessing it will never show up anywhere. But for now, we'll keep it here, and not forget that we're carrying such a possibly explosive number around. Huh? So, but aside from that, I can rewrite f as the integral. I still have the integral, the path integral over q. I still have the exponential of this exponential together with the exponential of the potential that I wrote at the start. So this will be the integral from t to t prime dt of q dot square over 2 t minus v of q t. And this you recognize, right? This is just the Lagrangian for this system, right? Assuming a particle of mass 1, right? So this is just the kinetic energy. So this will be qt exponential I t to t prime dt of the Lagrangian of q dot. So essentially what that Gaussian integration allowed me to do was to go from the Hamiltonian formalism to the Gaussian one, to the Lagrangian one, right? And finally, this integral of the Lagrangian we also know, right? This is the action. So the most striking result we're having here is that this propagator is actually a path integral which is governed by the action of the system. So I'm looking at all trajectories, and let me highlight this because this is important. Right? So what I'm doing here is that I'm looking at all trajectories that go from q to qt to q prime t prime, and each of these trajectories is being summed over, I mean integrated over, because I do this continuously. And for each trajectory, I'm changing. They are being summed over, but they are interfering with each other because they have this phase which is set by the action, right? And this is there's a complex version of the saddle point approximation here. I already talked about this, right? Which tells me that when this action is close to extreme, these phases will not change much. So S is not changing a lot if I'm changing the trajectory near the extreme of the action. So those trajectories will interfere constructively. So I have already some intuition here that these trajectories that are close to extreme of the action, right? Because the action will be different for each trajectory, right? They will dominate this sum because they all interfere constructively. While the ones where the action is big, I mean, are changing a lot, we'll have a phase that changes rapidly and might all cancel each other. But besides the trajectory given by this extreme action principle, right, there's also fluctuations around it. And the whole quantum mechanics is coming from the fluctuation, right? This is an amazing result. Both these expression and the one we had before for the Hamiltonian, this one, they are also very special because if you think about it, I'm writing a quantum, essentially quantum quantity and transition amplitude, right, in terms of a classical Hamiltonian, because when I was doing this process of slicing time in many parts, I was able to exchange the operators by their eigenvalues at each point, and I constructed a function, right? So essentially the function I'm plugging here is the classical Hamiltonian. Is the Hamiltonian with P and Q being just functions, right? Just momenta and coordinate. Right? And the same here for in the case of Lagrangian formalism. I'm just taking the classical action, putting inside this very strange integral that takes into account these fluctuations around the classical trajectory, which is the extreme of the action, and that's giving me a quantum behavior, right? It's totally possible to, I mean, to prove that this is completely equivalent to the normal quantization we're used to. We'll show a lot of examples. In fact, Feynman, which is the guy that came up with this idea, he did the opposite of what we did, because we started from canonical quantizations, right? So when we talk about these states, and we say that evolution of the states is dictated by the exponential of the Hamiltonian like that, we are assuming the Schrödinger equation, right? We are using the Schrödinger equation here. And we proved, starting with the solutions from the Schrödinger equations, we proved that you can write these in terms of this path integral. Feynman did the opposite. His intuition told him that the trajectory should be controlled by the action, by some exponential of the action in this way. And starting from this, he went all the way back and proved that the functions, the wave functions that can be obtained by this propagator satisfy the Schrödinger equation. Of course, when doing this, he was proving it only for the cases where you can actually write the Hamiltonian as a kinetic term plus a potential, right? But you see, it's amazing, right? He started from this, and this is as good as a starting point for quantum mechanics as the Schrödinger equation, which is very impressive. So finally, let me introduce a set of important objects that we'll be calculating all the time with path integrals. So imagine Again, we know that in quantum mechanics we're all the time calculating expectation values of operators, right? So take something like that would be the expectation value of this position operator on this state, right? So now I'm generalizing a little bit this object to include, a transition between different states now with this operator in the middle, right? And it's implied here that this time in which I'm calculating this operator is between the other two. So t is smaller than t bar, which then is smaller than t prime. So remember again that these moving frame states, they are eigenvalues of the position operator, but at the same time. So in this case, this guy is not the eigenvector of these operators because the times are different. So essentially what I'm calculating here is I start with some state, it will evolve in time until I get to t bar, then I apply this operator, and then I let the resulting state after the application of the operator evolve again until I get here. So that's the object I'm calculating. Right? So it's not exactly obvious right now what means physically to apply this operator at an intermediate time, but you'll see later that this is how interactions work. For now, what you can imagine is just I start with state, it evolves a bit, I measure the position, and then I let the resulting state evolve again until the end. So how do we calculate this in path integral? Right? I will use the same trick as before, right? When I was calculating just this. Right, so what I did was to insert an infinite number of intermediate times here, and then I wrote the whole transition as a path integral. Now what I do, I insert a lot of times here, a lot of times here, time slices here and here, until the number of slices is fine enough that I can identify this t bar as one of those intermediate times. Right? And the rest of the calculation is very similar. So now I'm again, if you take the time coordinates, I have t prime here, I have t here, and t bar somewhere in the middle, right, between them. When I start doing my usual slicing of time, right, with always again with step epsilon between any two neighboring times, eventually I'll get, assuming this is fine enough, right, it's really epsilon going to 0, there will be a ti that is the same as t bar. And then I continue the same way I did before, all the way to Tn and Tn plus 1. I'm doing exactly the same calculation we did before. I'll have a bunch of Qi, Ti, Qi minus 1, Ti minus 1 elements to calculate. I'll have a lot of these, but in the middle of the whole sum, there will be one where this operator appears between the neighboring states, because I'm always inserting, to do this slicing, I'm inserting completeness relations like this, right, with the integral. And eventually you'll have one where I inserted a completeness relation to the left of Q of t bar, and another one to the right. And I'll have these elements here. Right? That's the only one that is different. All the other elements that are just like this, I have already calculated. Right? We know how to get it. It will just be exponentials or have an Hamiltonian. The same thing we did above. For this one, there's a little change. So let's think about this one. It will look like this, right? I'll have, since I'm identifying t bar with ti, right, I'll have something like qi plus 1, ti plus 1, the operator at t bar, qi ti. And now I'm assuming that ti is t bar, and that means if I take ti equal to t bar, that means this now is the eigenvector of this guy, right? So, and this is the eigenvalue, so I can remove a q of t bar outside, or q of ti, doesn't matter. I'll keep t bar because that's how I mean that my answer can only in the end depend of q prime, and this q of t bar, right? So I'll write it like this. This is no longer an operator. This is the value. This is the eigenvalue. And once I remove this outside, what I have here is this, which is just another one of those many elements that I did before. Exactly the same thing we had before. So the only real change that will happen, I can go through all the same calculation that I went before, but I got this new guy on the block here, right? So I just got this. The effect of having this operator here is to have this function in the end. I just got a new guy showing up inside my integral. So now instead of having just exponential of the action, and also this guy just is a bystander when I doing the integral in the momentum, right? Doesn't do anything. It just sits there, and I can do the Gaussian integral in momentum the same way I did before. So I can basically repeat the whole calculation I did before with this guy just sitting there inside the integrals waiting for the end, right? And that means that the answer will be just this, right? So now I got this guy inside the integral. So instead of integrating just exponential of the action, I also have this function. But again, I am exchanging same thing that happened before. And I'm exchanging an operator by a function. Right? This guy becomes a function of position and this integral. But now I'm integrating on all possible shapes of this function, all possible functions, in fact. We can do the same, and this is simple, but there's one unexpected thing that happens when I take this forward. Now, suppose I take this same idea, but instead of putting one operator, I'll put two of them in the middle. One at a time t1 and another one at a time t2. So again, same idea. I start with this state, let it evolve, apply operator, evolve a little bit more, apply another operator, evolve more, and apply this other operator. And you know, to do this slicing properly, I have to assume an ordering here. Otherwise, I don't know how to do the calculation, right? So I'm assuming that t is smaller than t bar 1, which is smaller than t bar 2, which is smaller than t prime. Otherwise, I don't know how to do the slicing, right? I cannot go backwards in time if this. So I'm assuming this ordering. Again, the way I'll calculate this is just introduce a huge number of integrals here, which will then become path integral. So the result will be the path integral in all Q. This guy stay here. There'll be a bunch of intermediate states going all the way to some Q j plus 1 t j plus 1, the first of the operators. Then more states introduce qj, tj, so on and so forth, until I get to some qi plus 1, ti plus 1. This operator, and then I'll make this a little bit smaller, and then qi ti all the way to q1 t1, this state. Right, so I inserted everything that is in red here. So a number of identities here, a number of identities here, and a number of identities here. Right? Again, if this is fine-grained enough, in the limit I have very small time slices, I can identify T2 with Tj, which means I can remove the operator symbol from here. Same thing here, right? Once Ti is close enough to T1, I can remove this operator symbol here, which means these two eigenvalues now go out, and what is left is just a bunch of elements just like this one, exactly what I had before, including integration in momenta, everything. Now I just have these two numbers sitting here inside the integral waiting for the calculation to go through. And I get to the following result, right? In the end, what I get is that this guy is just the integral in the path integral in Q, exponential of the action, times these two numbers. And here comes a curious thing, right? Because as I said at the start, these two operators, they need to be ordered here as time is ordered. Otherwise, I don't know how to do the slicing. But now here, T2 and T1, they commute with each other because these are just numbers. These are positions, right? Functions of position, functions of time. So they can commute. It's not a problem, right? That is curious because I could actually, so I calculated this with this condition. Right? This is going in here. But I could also have calculated another object, which is this one. It's being difficult here. So this is T1, T2, right? In this case, I would have to assume a different ordering to do the same calculation. I would have to assume that T2 is smaller than T1, otherwise I don't know how to do it. Right? I have to slice now. The time must evolve from right to left here. But the result is exactly the same, right? Because once I turn these operators into functions, they can commute with each other. So the answer on the right-hand side here would be the same. Right? If you can just change the ordering here. That means that if I want to go from this side towards that, I have to decide, right? Is this expression equal to this one under this assumption or this one under this, right? And that's the whole point, right? If the assumption is the important thing, right? This will be the same as this expression when these two intermediate times are ordered like this, and this integral will actually give me this expression when the time ordering is the opposite. And the way we have to write this is that actually the path integral of with more than one operator like that will be given by the time ordered product of the operators. Time ordered product. And this is very important. And let me just define the time ordering here. So the time ordering of two operators is just the product of the operators and in this order when T2 bar is smaller than T1 bar, and this one when T1 bar is smaller than T2 bar. So ordering time from right to left. Okay? And you see the path integral takes care of this automatically for us. It's you just do the path integral in here. You don't have to worry about the ordering, but you always be calculating the time ordered product of this. Right? This can be generalized. We can do this with more operators. I did just for 2. I could do with 3. Then there are 6 possibilities. I could show that for each of these possibilities I could only calculate the time order version, but the result on the right side will be the same. Everyone can guess by now that I will just appear another operator, another function here, right? Because the calculation is pretty straightforward, right? Not much changes if I have many operators in the middle. So I'll write the time ordering for, in this case, will be just a time ordering of many operators all the way to some operator calculated at time n, capital N here. And this is by definition just the product of all these operators ordered accordingly, right? In this case, I'm just putting this. But whatever I change the order, I have to change the order here too, right? And then I can define the objects I want to define here, which are called the endpoint functions or the correlators of endpoints, and which are these Gn, let me use small n here, Gn of a number of times. So there, it's a function of many different points in time, in particular n points in time. That's what this n indicates here, is how many operators I put in the middle. This is defined as this transition of the time ordered product of n insertions of the operator. Which then I know how to calculate in terms of a path integral. So you can use this as a definition, or the path integral itself as a definition. It's completely equivalent. Of the product. In this case, we just have functions here. And these will be the correlators, and these guys will play a major role when in this case I'm just doing quantum mechanics, right? There's no field theory here yet, but will be very analogous for field theories, and these guys will play a major role in quantum field theory, because as I said, this is the physical story I'm telling here. Is I start with a state, I let it evolve in time a little bit, then I do something with it, right? In this case, I measure the position, but these will be interactions in quantum field theory, and then evolves a little bit more, another interaction, evolves more, another interaction, and we will use that to actually predict interactions of particles. And so we will be using these correlators all the time. So very important object. Later will also become more clear why I call them G. They are, some correlators are green functions, so it's, we'll take a look at that later. So that's all for today. See you next video. I mean, you see me next video. Bye. Okay, we have just one exercise for this lecture. This is actually a very simple exercise, but with an amazingly low success rate. So do it with care. It involves taking a Lagrangian, writing the Hamiltonian, the classical equations of motion in the Hamilton formalism for this, and then writing the propagator as a path integral in momentum, and with both momentum and position path integrals. But pay good attention to what exactly that expression we derived for these path integrals mean when you're doing that.